Culture. Sir, stage is yours.
आएगा
Am I audible without mic? I don't want to my head busy. So am I audible in the last row? Listen. Okay, good. Are you recording or something? इसकी जरूरत नहीं पड़ेगी। ठीक है। Okay, so again I'm asking, are you audible in the last batch there? If you're not listening, you may be busy. If you're not listening, otherwise it's fine. Okay, so the topic is chip scale optoelectronic devices based on semiconductor heterogeneity. So I don't work exactly in agriculture related applications, but whatever devices we are working on, they can be applied as a sensor. So, to detect, let's say, some infections in the seeds or any other, crops. So I'll touch upon some of the sensing applications also. I belong to, I established this laboratory called ONRO or Optoelectronic Device Research Laboratory. And I'm from Department of Electrical Engineering. I also belong to Center for Advanced Electronics at IIT Guwahati. So my talk will be primarily, it will revolve around optoelectronics, some part of semiconductors and photonics. So this picture here is your data center. The data center, especially, I'm beginning from Corning. Corning is the well-known industry to manufacture optical fibers. And these optical fibers are not necessarily in your telecom, but it's there in your data center. So here you see all these yellow connections, yellow wires, they are fiber optic cables. And the red color is COPS. So in contrast to the previous versions of data center or telecom, where mostly you have copper connection, but now it is optical fiber connections mostly. Right? Okay. And another picture here is the high performance computer from IBM. This shows you all these orange colors here. You see these orange colors in this whole building. They are optical fibers, and if you estimate the cost is around 10% of the total system cost. So that means your optical fiber connections, they are not necessarily in city to city or in long distance communication. You are using it for even small scale or short range applications. This is a high performance computer whose applications are in weather forecasting or predicting the stock market or stock or simulating protein folding or any other biological simulation. Where you need very heavy computation and a normal computer may not work there. That's why you need a very high performance computer, and you utilizing light for that is very beneficial. I'll talk about this later why light is beneficial. So this was actually installed in I think some naval laboratory by IBM. So let's see why where the light is used, different application technologies for that. So it's there everywhere in form of the normal light which we see, which enlightens us, our night basically, and like it's not properly working. It's a lag. You will be doing it. So for example, this picture down here is your very small laser or LED which is used in different applications. Next. Okay. So the light-based technology of photonics had widespread applications. For example, it's there in transport. When I say transport, it means communication, data transport. I'll be touching what property of light is very beneficial for that. It's there in storage. Storage is again data storage. For example, your CDs and DVDs, where you were driving the information using laser beam and you were reading your normal CDs and DVDs, you still see them around. Right? Then it's there in sensing, remote sensing, where without touching the object you can detect them. Then it's there in computing and processing, just like communication. It's there in displays, your LED and LCD based, they are also dependent light-based technology. Then it's there in energy, from a solar cell or from a photovoltaics, it's there. Then it is there in actuation or other industrial applications like laser-based welding and cutting. Those are, and then medical diagnostics. We have many kind of optical machines which are used to diagnose different things related to medical field. So see, it has a widespread use. And one of the very hot application of light is in communication. And when we talk about communication, we should not talk about the contribution of Graham Bell, who invented photophone transmitter and receiver, which revolutionized the whole information era. Right? That was the start of the information. And solar cell, that I want to talk about this. Then another thing is manufacturing of semiconductor chips, ICs. There is a very important technology called lithography or photolithography optical, where you shine the light on silicon wafer to pattern, to layout, transfer the layout of, and that layout may be your different portion of the transistor, casings or electrodes or so on. So that is another use of light. So because of this widespread use of light, many governments across the globe, they have recognized photonics that it is of economical importance. That's why it's nationally important. The US, Europe and India also have recognized it as nationally important. I hope there are some students also. So let me tell you some of the basics here. As I said, one of the hot application of light is in communication. So when we talk about communication, basically we talk about electromagnetic spectrum. I hope many of you are aware of that electromagnetic. This is a high frequency, and if you send high frequency waves to this operant atmosphere, they will not be that much disturbed by So in this electromagnetic spectrum, the frequency is increasing as I'm going from left to right. Right? It starts from radio waves and crosses microwaves, millimeter waves, then comes the infrared light, then comes light, UV, X-rays, gamma rays and so on. So frequency is increasing in this direction. Right? So So in communication, basically, they are electromagnetic waves. They are associated with electric and magnetic field, and they are transverse fields. So you've been using microwaves in antenna or RF for antenna. So there is an important fact. The fact is that your information carrying capacity is proportional to carrier frequency. So normally what is the use of electromagnetic waves from here? That you can modulate them. You can load your information onto them and then send them. For example, I am speaking with you and you can hear me. But what if you are in a distant place? Then I need to load my voice onto some truck, get it, and then I will send it. Then you are modulating. So higher will be the frequency of these carrier waves, more information you can do. This is a fact. Right? So that means, what if you are communicating at radio waves and then you jump to microwave? So you have increase in the frequency. Right? Because of the increase in frequency, your carrying capacity, information carrying capacity will be more. That's why there was need that you go and go towards higher and higher frequency. So what if you further go till very high frequency like light? If you communicate at light, you have very more increase in the carrier frequency, more information. That is next. No, previous. Okay, so then people wanted to use light for communication. And if you're all mics not lights.
So if you're using light as a carrier wave, this is called optical communication, right? And what is the benefit? The benefit is that your bandwidth or information carrying capacity will be enormous. Well, you cannot compare. Then you can ask, why not further high frequency like UVs or X-rays or gamma rays? The reason is that, to make communication chip, your transmitter and receiver should be almost chip scale. So you cannot detect and generate X-rays or gamma rays which are chip scale. They are really bulky. You have seen the X-ray instrument somewhere in medical research. It's very bulky. So whatever this radiation range you choose, it should allow you to make the system which is chip scale. So till light or even till UV, it's fine. So that's why optical fiber communication has revolutionized this information era. Because with light you have enormous bandwidth, really enormous, right? So this is about long distance communication. Next please. Yeah, stay. That's all. So basically when you're talking about light-based communication, you send the light through open atmosphere, there may be atmospheric disturbance which will disturb the light. So that's why for longer distance communication, which is light-based, you need a carrier, you need a medium for light. And that medium is optical fiber or glass. So people found that in 70s or 60s that glass can be stretched like my hair or your hair, and you can make it wider. And the glass is normally transparent to the light. So the attenuation of glass or the optical loss of the glass for this wavelength range, 0.8 micron wavelength to 1.7 micron, is very less lossy. Attenuation is very low in that range. That's why in optical fiber communication, this wavelength window is used. Right? This wavelength window is used. So you are using light as a carrier wave and you are using glass fiber to guide the light. Then this all together package is called optical fiber communication. Right? Next please. Okay, so now light is the enabler of advanced technology. Light has, as I said, it has many uses. Right? So once you're talking about high performance computing, or you're talking about AI, or you are talking about neuromorphic computing and even quantum computing, you basically need improved or new hardware, because your existing processors may not be sufficient. They will not be able to handle the heavy computations. So you need some alternative technology, or maybe alternative transistors, which is very different from the current transistor which is there in your pocket, in your mobile phones or your bags and laptop, right? So you need improved computing hardware when you're talking about even biological simulation or any other thing. So there are many ways to do that, and one of the way is to use the light for information processing and for computing. For information processing, we have been using it for communication, and now it is entering to short reach and even coming to the processor side. So you want to process the information and compute with light, because why? What is the reason? The reason is enormous bandwidth, which is not there with any other spectral feature, right? So if you do that, there are plenty of platforms. Like once it comes to semiconductors, we know that silicon is there. Why silicon is there? It is abundant, and because all your processors, they are CMOS based. I hope everybody is aware of CMOS. It's basically combination of N-channel MOSFET and P-channel. CMOS based, and the MOSFET can be made because of MOS, MOSFET, oxide. So silicon can be easily oxidized. So it gives you easily, easily manufacturable transistors, which is metal oxide semiconductor. So semiconductors oxide is necessary for MOSFET. That's why silicon can be easily oxidized. So you use silicon to make MOSFET, and all your CMOS based processors are based on silicon. So you have silicon, and you also have some other devices for optoelectronics, for example, gallium arsenide, indium phosphide, and so on. So you need to have ultra low loss waveguide where you can guide the light on the chip. You can have individual devices which are compatible with your transistors, and you go towards hybrid integration, then different material platform integration, and so on. Then you realize some ICs there. That is the journey you have to go through if you are targeting computing with light. That journey has to be there, right? Next, please. So looking at the importance of these things. So the government of India has, I think several years back, they have launched this India Semiconductor Mission, and they are targeting their semiconductor fabs and display fabs. Display fabs for the screens, for TV or computer screens, and semiconductor fabs to manufacture ICs in India. And there will be establishment of high-tech clusters in different areas related to semiconductor. There will be, it's already taking place, this research ecosystem is there, and they want to modernize and commercialize semiconductor laboratory, which was initially a company, public sector company, then it came in under ISRO, then it is under Ministry of Electronics and IT. So they want to commercialize, because SCL Mohali, it is situated in Mohali, Punjab. So it has the capability that it can, fabricate some of the low-scale ICs. The Vikram 32 recently, for space applications, the SCL has manufactured that IC there. You might have seen it in the news there. So they also are planning to uplift the SCL with some joint venture like TSMC or Global Foundry or Samsung, probably, in form of a commercial fab. And there are at least many areas, and 4 of those areas which government has recognized are these: compound semiconductors, because silicon alone cannot do everything, so there has to be some other semiconductors. There is this silicon photonics where my laboratory is also working. Then there are sensors and MEMS for different applications, including sensors for agriculture application or biological application. There is this semiconductor design. This semiconductor design has been there very strongly in India. Like the bigger giants, industrial giants, they have very big design centers in Delhi, Bangalore, Noida, Gurgaon, and so Hyderabad. So they do design here. So most of the chips have been designed in India, but they were getting manufactured somewhere else. But now the government has pushed that you should manufacture them here. That's why Tata has, I think, come up with some foundry there. And the idea is to, of course, innovate, propel the innovation and build domestic capacities in that area. And it will, of course, have good effects on our economy. Next, please. Another related mission is quantum mission, where there are several 4 hubs there, which is one is there in quantum computing, where you want to build kind of quantum processor. There is one quantum communication. There is one in quantum sensing and metrology. Another one is quantum material devices. And my laboratory is also taking place in quantum computing there. So in these also photonics is there as an important pillar. Next, please. Okay, so I was talking about long distance communication based on light, right? So when the distance is multi-kilometer or less than that, we have been doing already. So I think this campus will also have some optical fiber connectivity, but that connectivity is several kilometers or so. Now the light, you want to transfer the data with light, and the trend is towards shorter links. Shorter links, not even 10 meter, not even 1 meter, even less than that, maybe in centimeters or millimeters. When you want to communicate at millimeter, what does that mean? Communication at millimeter distance. That means you are on chip. You want to use the light inside your processor or inside your racks, telecom racks. That's where the trend is. And you want to put optics as close to the processor as possible. Processor means a computing processor, right? So you are talking about shorter distance, you are talking about higher bandwidth density, you are talking about higher state of integration, and maybe integration of light-based devices with electronic IC. That's what you are envisioning towards, right? So next, please. So this is one chip this is an optoelectronic chip, photonic chip from Intel. I think 15 years back they have demonstrated it, and this is being used in data centers almost everywhere. This is a light-based chip. So where you have CMOS circuitry there, if you see there, CMOS circuitry is there. You have photodetectors which will convert the light into electricity. You have lasers, electrically controlled laser which will voltage based light they will give you. You have modulation which is optical, everything is there. And because light is there, so being electromagnetic waves, its control is with Maxwell's equation. Because light is an electromagnetic wave, so to study the propagation of light, you need Maxwell's equations. And to generate the light, to detect the light, to control to some extent, you need semiconductor electronics. That's why, so if you're working in photonics, you need to have the understanding of semiconductor electronics as well as electromagnetic waves. So, right? Next, please. So, when this optical communication was evolving, so the idea was to build the sources of light, to detect the light. There should be chip scale, they should be as small as possible, the size. That's why people started looking towards semiconductors. Why? Because unlike conductors, unlike insulators, you have some control there. And in electronics, there are 4 things. People will say 3 things, but the 3 things, what are the three things in electronics? The one is the size, as small as possible, you always want. In electronics, right? What is the other one? Power. Low power consumption. That is the second one. What is the third one? Speed. That's where you chase these things. Size, speed, power consumption. The another thing is control. you in electronics you always wanted control and more control and more control. You always wanted that. So conductors and insulators couldn't give you that control. Semiconductors gave you, because you can control the flow of electrons at your wish by controlling the doping. Intrinsic silicon was not sufficient, that's why you made it N-type or P-type, and then you joined two differently doped semiconductors, N and P, right? You had, so that you have better control. Then was the diode N and P joint junction diode, was that enough? Were the two terminals enough for you? You were looking for third terminal, and what was the name of the device? Transistor. So that from one terminal you give input, from the third terminal you collect the output, and the middle terminal you use for control, right? So that's why when it was evolving, there was a need that you have light-based sources which can be built from semiconductors. You have light-based detector. You should be able to detect the light on chip. There should be semiconductor based, and luckily that technology was there. So when you think of light emission from semiconductor, you use PN junction, which is forward bias, right? And your LED is based on that. How? So you forward bias the LED, you take PN junction diode, you forward bias the PN junction diode, what will happen? Holes will go from P to N, electrons will go from N to P, and because of the generation, because of this recombination, the added energy will fall, the electrons will fall there, and you have spontaneous emission. Your LEDs are based on that. If you stimulate this, use stimulated emission, and then use some mirror on both sides of this optical generation, then it becomes laser. So stimulated emission plus optical amplifier, you have more and more numbers per one pass, more and more photon numbers, so this becomes laser, right? So this is completely semiconductor based LED and laser, and they are the most common optical sources used in your communication, data centers, computing and so on, right? Similarly, at the other side you have reverse bias PN junction. So that means you are giving the voltage, electrical injection, and the light is coming out. So light generation. Here is light detection. You shine the light on a reverse bias PN junction. What will happen? When a photon incident, it will generate electron hole pair, just like that, and that electron will go towards N side because it's a reverse bias one, right? Reverse bias means electron will go to plus side, that N side. So you are increasing the leakage current. So more photons, more electron hole pair generation, more photocurrent. We call it photocurrent. So that means output of detector is electrical current, photocurrent, which is based on, depends on how much light you have shined. So for optical transmitter, what do you need? Optical transmitter. Optical source, you need light, so you use this one. It will transmit the light. Transmitter. In optical receiver, you need something which can detect the light, which can convert the light into electrical one. You use this. So this becomes optical transmitter. This becomes part of optical receiver, right? So we have basic things with us now. Next, please. So, okay, this is our traditional long range optics, which is, the distance is 10 kilometer or even 500 kilometer. City to city or data center. Let's say Amazon have data center here and we have another data center at some few kilometer distance. So they may be connected by optical fiber. So that has been there, and now you are slowly decreasing this distance, and you are already there in the racks. In the starting I showed you orange color high performance computer from IBM. They have replaced this copper. Where the copper is used now? For interconnects, for VLSI interconnects. all your processor inside your mobile phones or laptop, you have copper connections, IC to IC. Different ICs you might have, those ICs are connected by copper, electrical connections. You want to replace that electrical connection with optical connections, and that is called optical interconnects. That is new area people are looking at. So even if you are looking at optical interconnects, there you may have optical transmitter and receiver. It's not like you replace the copper and put optical film there, optical fiber there. You have to have counterpart components, optical components there, just like I showed you, laser, LED or detector, right? They have to be there. So you are slowly coming to the chip, which is optical. Next please. So this is another very important laser. This is also PN junction based laser, but this is called VCSEL, vertical cavity surface emitting laser, which was invented by my institute in Tokyo Institute of Technology. So this is called VCSEL. It vertically emits the light, and it controls by top mirror and bottom mirror, which are purely semiconductor based mirrors. So you have light which is back and forth, up and down, and light finally laser will come out from the top. So this is used in data centers. Almost all the data centers you have this. In Xerox machines, in optical mouse, it's there. Next please. Next please. Okay, so this is another component which is used in data center is this active optical cable. It's a kind of this kind of plug in or plug out. You have long connection of fiber where optical fiber terminates here. Let's say this is the data center, it terminates here. You will plug in this. So what it will have? It will have some multimode optical fiber which will go into your rack. So it will have a VCSEL, a special laser, and a photodiode in it, and there is some whole package there. So using a semiconductor laser and photodiode there. Next please. So okay, so you look at these modules, 1550 nanometer, 100G module, 1310 nanometer, and all this growth year by year, you are slowly coming optical fiber component, then inside the rack, and then this intra-chip, on-board and intra-chip. The meaning of intra-chip is not chip to chip. Inside a common chip, you wanted to have optical connections. It may feel like the two transistors are connected optically. It's not possible now, but just you imagine this. The transistor to transistor connection is optical. So what benefit you will have? Light's benefit, enormous bandwidth, and this is the answer to all these, the 5G, 6G, and your video conferencing is because at the back hall, at the long hall, you have light. So same benefit from the communication you want to take on the chip inside your computer. That's what you want to do that, right? Next please. So Intel and IBM, they have been, interestingly doing great in this area. Like, you have light-based sources, you have photodetectors, you can have optical modulator, and so on. And you want to have this kind of hybrid integrated chip, which was already built by many companies, especially Intel. And the future is this: when you want to have everything, including CMOS chip, on the same one chip. That means it is fabricated in one foundry, not hybrid integrated like this. In hybrid integration, you have fabricated, manufactured one IC there, another IC there, optoelectronic IC there, and then you hybrid integrate them. You bond them onto a common platform. That's what you do in hybrid integration. But here you are doing it in monolithic way. So this is the future. Many R&D labs and industry, they are working towards that. Right. Next please. Okay, so the application of these things are in data center. I've been talking about autonomous cars. It's there in high performance computing, which includes, as I said, some kind of biological protein folding, or so biological computations. It's there in sensors, in aeronautics and space, in telecom, it's there. Next please. Next. Okay, next. One more. Yeah. So you have light-based source. You are able to generate the light with semiconductor. You are able to detect the light with semiconductor. Similarly, you want to modulate the light. You don't want electronic modulation here. Because you are already at optical domain, you don't want to convert light into electrical domain and then put electronic modulator there. Because electronic modulator will have bandwidth limitation, unlike that. So that's why you want to directly modulate the light, produce ones and zeros in optical form. That's where this optical modulation comes into picture. So there are many techniques. So like in my laboratory, we are thinking of silicon with some other semiconductors to realize ones and zeros. Right? Next, please. Next. That is your doctor. Yeah. Okay. Fine. So once you are looking at very high scale integration with light, just like in normal electronic chip, you have billions of transistors, right? Billions of transistors on the same chip. Similarly, you cannot have billions of photonic devices on the same chip because the size is still limited with the light. So that's why you need to learn a lot from semiconductor devices. For example, you look at here, this graph here. It is the size on the y-axis and production here. Initially in 70s, your node was several microns. And what is the node? Node you can consider your channel length in your MOSFET. I hope most of you are aware of MOSFET or so, right? Transistors. So it is that. And slowly you have in 80s, you have 3 micron and so on. In 2000 or so, here, you have almost 0.3 or 300 nanometer node, photolithographic node there. And beyond 100 nanometer, it was late 2000, people called it the era of nanotechnology. Beyond 100 nanometer, less than 100 nanometer. So then they were shrinking, reducing the size of the transistors, and around 20 nanometer, 19 nanometer size, channel length, they found that your existing transistor design is not enough. So till then, from the starting, your CMOS was evolving. That's why this era till 19 nanometer, so you call it evolutionary CMOS. Normal CMOS design was enough. But beyond 19 nanometer, less than 19 nanometer, what happened? That it becomes revolutionary CMOS. So what is the biggest problem? The biggest problem in transistors is, I hope you know source and drain and the channel between them. Most of you, right? Inside transistors, those who are from electronic background. So once you are decreasing this channel length, that means source and drain are coming very close and close and close. And you want to have separate bias on the source, separate voltage bias on the drain. But when they are really close to each other, you put bias on the drain, it will affect the source. This is called short channel effect. They will no more be independent. They will affect each other. You don't want that. You still want that transistor should behave like transistor. The one bias should not affect the other. So that is the problem once you are reducing this size. It was microns, then it was 100 nanometer, then it was less than 20 nanometers. So now you have problem. That's why the industry and the bigger R&D labs, they have to revisit the transistor design. And then came FinFET, if you have heard of it. And this was a new transistor, FinFET. So FinFET and the nanowire, nanotube and so on, that becomes new designs of transistor, and that era is called revolutionary CMOS. So in basically electronics, whenever you want to improve the performance, whenever you want to open up new applications, for example, you you may want to detect at very early stage some disease in the seeds, crop seeds or so. So early stage means you have to do some nanoscopic sensing. And for nanoscopic detection, you need really small scale devices, small scale sensors. The sensors which has very low detection limit, right? So that's why you want to open up new applications. So either you change the material or you change the geometry. That's what people have been doing it. And that change can be at micro scale or nano scale or at atomic scale, right? So imagine you had intrinsic semiconductor and then you made doped semiconductor, then you make diode, then triode or transistors and so on. So all this is called device engineering or circuit engineering because you want to improve the performance or you want to integrate new applications with your device, right? Next please. Next. Okay, so we have at IIT Indore we have this Center for Advanced Electronics where we are working on smart materials, technology, devices for computing, for advanced digital memory, for interconnects, for medical and biochemical sensing, and this includes agriculture. Not me, but there are some faculty members who are working towards agricultural sensing. Some of them are they are monitoring the hazards, for example, fire in forest. Some of them are detecting at early stage some diseases in soybean crop and some other things. So soybean, we have in Indore Soybean Center from Agriculture Institute. So some of the faculty members from our center, from our institute, they are connected with the scientists in that soybean research center there. So we are very much we are very much open to collaborations and help. So we are building our capacity in semiconductor technology, and we are creating the manpower for national semiconductor needs, and we are running PhD in advanced electronics, MS and these things. Next please. So we have number of laboratories in that center. You can see there are nanoscale devices, then software, signal analysis, material and devices, so many. So if you're interested, you can just go to IIT Indore and type there Center for Advanced Electronics. Next please. So this is my laboratory, what we do in IIT Indore, and we call it Optoelectronic Nano Device Research Laboratory. And we are working for advanced devices for next generation optical communication interconnects, and also we are also working on optical biosensing. When you say optical biosensing, it includes some problems in food, for example pathogens. So we are optically detecting pathogens in food, foodborne pathogens. Yeah. That is one area we work on. So next please. This is my group. I have this Ramanujan fellow with me, then 2 postdocs and several PhD and MTech students, and 4 or 5 BTech students are working in this area. Next please. Okay, next. Okay. Next please. So we have, this is one kind of sensor which we have developed. So this is an SOI chip, a silicon wafer special chip, and we have created a nanoscale comb there. So you have this kind of comb structure, then you have a cavity of length LC and then another comb. The spacing between the two combs is called gamma 1 or gamma 2, and we can adjust this spacing to realize a very narrow peak there. You see those peaks there, the BRW means band rejection window. So if you put some analyte there over this region there, any analyte including your pathogen or some agricultural sample. We have not tested agricultural sample yet, but let's say you have some soil there, right? You put the soil there, very small amount of soil. It will give you some output in form of transmission versus wavelength. if it is a normal soil, its refractive index will be something, right? So it will give us some output. Once you put infected soil, there will be some changes there, some changes in optical properties of that. And so we build our devices, we design them so that those infection dependent changes becomes more and more. That's what we do design. So similar device we have tested for pathogens, foodborne pathogens, especially E. coli. So you put E. coli there, and we could detect the presence of E. coli optically. Next please. This is for space application. So for that please. Next. 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 Yeah, this just to show you that this is I think from Intel. So Intel was the first in industry to develop a transceiver, transmitter receiver on the same chip based on silicon photonics. So that means, and now they use that silicon photonic transceiver chip for high performance computer. So they say they are making it specially for AI. For AI processors, they are using intermediate optoelectronic connections there. So whatever I talked about is not the future, it's very near. You will see them. You will see optical connectivity on the chip very soon. Next please. Okay, next. Okay, so in my laboratory we have been working on different devices, especially at sub-micron scale, and we are using engineered silicon to make different like modulators, optical couplers and optoelectronic filters. And also we are working on two technologies. One is based on non-silicon, which is zinc oxide. We are making devices based on those material platforms, and also we are making based on silicon and ITO, some of the devices. Next please. Okay, so this was one simple device where we know that silicon cannot do everything. So that's why we were in search of some other material with silicon. For example, if you have heard of the Moore's law in electronics, right? Moore's law in electronics tells you that integration of the transistors, number of transistors in an IC will double approximately 2 years. So that Moore's law, people say that it is coming to the end. That's why they are revisiting the transistor design, or they are looking for, or they are exploring the new materials, which is other than silicon. So that's why in our laboratory, we want to hybridize silicon with some other semiconductor, which is for the future. So we found this ITO there, very popular material, indium tin oxide. And what we did, this is an SOI wafer. We have this gray color silicon on top, and then green color ITO. So what it does, when you apply voltage, there will be some electrical changes in ITO. And when you send the optical signal, there will be changes, voltage induced changes in the optical signal. That means you can make some optoelectronic devices with that. Next please. So we tested this next. So we tested that structure, and we found that once you are working on chip-based photonic devices, you know that you are at optical fibers. So optical fiber will come here, and you have to, from optical fiber, you need to take in this light efficiently. So you need to have separate chip scale coupler there, input coupler, which will efficiently couple in the light. And whatever you want to do with the light, you do that here. You want to detect it, you want to filter it, you want to modulate it. And then when you are done, you take the light output to output optical fiber. That means you need separate input coupler and output coupler. And this trend has been already going on. So we wanted to get rid of this kind of design. So what we thought, can't we make these input and output coupler part of your middle device so that you don't have to have separate input output couplers? Next please. So we built this kind of design. It's a silicon ITO based consecutive periodic design, which could give us input coupling, output coupling and modulation all together in one device. So we fabricated and tested this in our lab. Next please. So this was the fabrication done. Next. Yeah. So then the same device we could do, next please, for all optical modulation. So once you change the optical input power, there will be changes in the optical output power. So that means all optical process you could do with the same design. Next please. Next. Next. Yeah. So another thing, especially when it comes to biosensing, right? So your normal photonic devices are of several micron in size. So I think I will take 5 more minutes. So there is a trend that you want photonics at nanoscale, and with light it has diffraction limited size. So if you try to focus the light inside a size which is less than lambda by 2, or you want to take out the light from the size which is less than lambda by 2, you have diffraction limitation. So you want to beat this diffraction limitation problem there. So that's why there is a need that you try to manipulate the light at real nanoscales. You want to have very strong light-matter interaction, especially for sensing applications. And you want to exploit the exotic behavior of some nanoscopic or nanoscale materials there. For example, plasmonic materials there, right? Next, please. Next. So we build this plasmonic absorber there. That means if you take the light in, and this is your plasmonic absorber, which is electrically controlled. So light absorption changes. So that means even if you put some analyte there in between, you can detect the presence of that analyte, and even you can detect some of the problems in that analyte there. Let's say, as I said, maybe infected biosample or infected soil or any other sample there. You can do that. Next please. Next. One more. One more. Yeah. So in that plasmonic design there, we had this kind of taper structure. You take the light in, and it is at micron scale there, and it becomes at little less than 100 nanometer at the output side. And your silver-based, electrode-based device is basically your plasmonic device, so hybrid plasmonic device. So its overall size is less than a micron. And you could do that, you could have the switching. That means you can realize high intensity of light and low intensity of light using resistive switching. Next please. So we tested this, and we found that there is this 35 dB extinction ratio. Extinction ratio means there is an optical on there and there is optical off there. So between optical on and optical off, there is this 35 dB separation is there, which is very good value. Next please. Next. Yeah, so finally I think this should be the last slide or so. So we could build this nanophotonic circuit, which is a nanophotonic chip there. It has several optical inputs, several optical outputs, and you can do whatever you want in between. If you want to have more wavelength channels, you can do that. And what you can make an assay. That means you can make array of sensors there. For example, all these devices there, all these blue color devices, they may be your nanophotonic sensors. So you can parallelly you can detect number of samples. You can do even at nanoscale. You can have number of soil samples or soil samples or biological samples. So this we are now pushing it for some biological applications. Next please. Yeah. So finally, we have used these semiconductor junctions, especially to address the problems of silicon photonics. That is one thing, and we are doing integrated nanophotonics, especially sub-wavelength confinement for new applications including biochemical sensing. And the way forward is minimal change CMOS process, because you cannot randomly choose any material for your device or circuits. It should be fabricable, it should be compatible with the foundry scale or so. And we are also looking at some advanced transistor architectures where light can control some of the electronic signals here. Next please. Next, last one. So these are the 4 categories of our devices. Like we are working on some FinFET and MOSFET, advanced transistor architectures for light-based optoelectronic devices. We are also building this multi-wavelength nanophotonic chip, and we are pushing this chip towards biological samples, and we are using semiconductor heterojunctions for all our devices. And finally, this is especially this one we are doing it, we are making this device which is already almost ready for cancer detection, especially for lung cancer detection. So at very early stage, we are able to, in our laboratory, it's a prototype we are working on. At very early stage, we are able to detect the lung cancer based on semiconductor heterojunction devices. So last slide, I guess. Thank you so much. So we are always open to PhD positions. So if you are interested or in collaboration, if you want to visit our lab or anyone, just look at the web page and you can contact me or any other faculty member. Thank you so much. Is there any question? So it was very short time for me. So the last program went. Yeah. Any question? Semiconductor? Okay. Pure material. I've been the wrong person answering that. The one thing is political will. Now we have political. Abhi rajnitik dabao bhi hai. The government is pushing very hard. Abhi tak what we have been doing, we got liberal in 80s. Liberal means वो बाहर की मशीनें आने लगी. पहले बना रहे थे हम, काफी कुछ बना रहे थे. You know ITI means Indian Telephone Industries. वो लोग अपने काफी टेलीकॉम के इंस्ट्रूमेंट बनाते थे. वो बंद हो गई. और बाकी कुछ और मैन्युफैक्चरिंग प्लांट्स थे, वो बना रहे थे. But suddenly the government had opened up the rules for the international companies, so they came here. That was one reason. Another reason is we became a little lazy. जो टैलेंट था वो कहाँ चला गया? उसको एक चेयर दे दो, डेस्क दे दो, कंप्यूटर दे दो, दैट्स इट. Computer science or even civil engineer, mechanical, everybody was doing earning for the companies outside, Google, Microsoft and all software based. So वहाँ थोड़ा talent ज़्यादा चला गया, तो हम थोड़ा देर से आए, but still we came, and then in electronics design शुरू हुआ. Intel's biggest design center was in India, in Bangalore. So electronic design we have been doing it. So we were designing the chips. We are designing the chips. Manufacture अभी नहीं हो रहा है, but अभी क्या है? Assembly हो रही है. The Apple has one plant in Noida. They are building. The processor is not yet made here, but you will see that the processor will also be made. Tata has one foundry in Gujarat. They will open up and it will be functional very soon. Likewise, they have some assembly and packaging facility in somewhere in Karnataka, in Assam, like that. So we are into that. We don't have full-fledged foundry yet, but we will see it very soon. अभी क्या political will है, और तुम जैसे बच्चे भी आगे आ रहे हैं, taking electronics in their hand and there. So we don't want many softwares now. We want products, electronic products, or mechanical products. Because again there was politics involved. They were not given free hands so far. पहले वो I think they were public sector company SCL. फिर वो इसरो के अंदर आ गए तो सिर्फ इसरो के लिए काम कर रहे थे small ICs. But now when it came under MATI, they had the mandate that because they were already working towards some ICs for space application. This was the first one, 32-bit processor for space applications. इतना दिन इसलिए बनने लगे क्योंकि वो they had their own pace, वो उस स्पीड से इंडस्ट्रियल तरीके से काम नहीं करते थे so but now they are doing good. Any other question?
Thank you, Dr. Mukesh Kumar sir, for sharing your valuable knowledge and perspective. We deeply appreciate your time and effort. Now I invite our FDP coordinator, Dr. Nitin Kakre sir, to present a token of appreciation, a moment due to Dr. Mukesh Kumar sir. Thank you, sir. Let's gather for a group photo with our expert to capture the moment and celebrate this academic exchange.
पूरे नहीं आ रहे।
Thank you so much. Now, may I take the pleasure of inviting our respected guests along with all participant members to join us for the lunch in building number 3, room number G003. Thank you so much. After the lunch, the second session will start at 2:30 at building number 3.